Hello everyone, my name is Fatemeh Javidan. I am a lecturer in structural engineering at Federation University, Australia, and today I will be presenting my research on the lateral cyclic performance of hybrid fabricated beam columns. So for many years, cyclic design of hollow sections has been dominated by the use of mild steel. Obviously, the yield strength of these values of these steels are less than 450 megapascals, and usually the use of high-strength steel has not really widely been used or investigated in the literature. There are available studies on the cyclic performance of high-strength steel, which are mainly limited to yield strengths of up to 700 megapascals, and there have also been recent studies on a concept which is dual steel frames or dual steel members, in which a combination of mild steel and high strength steel is used for the building components. For example, the dual steel building frames with high strength axial load bearing members and mild steel beams providing that ductile mechanism, or eccentrically braced frame members which have high strength steel for all of the members, which will not produce any plastic deformation, but still mild steel is used as linked elements for the energy dissipation mechanism. And also high strength steel used along with sacrificial beams. Again, this is a study that the high-strength frame is used with mild steel sacrificial non-compact beams to act for the inelastic behavior of the structure. Borrowing from those dual steel ideas, this research proposes or presents a combination of two materials, high strength steel and mild steel, within the cross section of the component. So the beam columns have the two different materials. The plate elements are mild steel, and you can see the important material specifications are listed on the slide, as well as the tube elements, which are extracted from high strength steel or HSS. And also you can see the material properties of these two materials are shown, with a significant difference in the peak load and also the ductility or the deformation at UTS, and ultimate load is significantly different between the two materials. In order to be able to produce a model to simulate the performance of this dual section or hybrid section, some experimental results were used in order to build a model, a numerical model. And from these experiments that have been considered are lateral cyclic loads, in addition to 25% axial load on these beam columns, as you can see shown in this figure. And the cyclic loading is applied is a unidirectional load, which is applied in one direction, and it is according to FEMA 461. The parameters that are used in the model have been based on obviously the non-linear material and also geometry of the beam columns, but in order to be able to exactly model the material, the two or dual steel materials that are used in this section, combined isotropic and kinematic plasticity models are used. And these have been extracted based on experimental dog bone specimens which have undergone the cyclic loading. So this slide specifically shows the kinematic hardening model that has been used, and the kinematic hardening parameters C and gamma, which you can see are obviously calibrated using a single stabilized cycle in both materials. In this figure here, you can see how the softening, the red dashed line shows how the high strength steel material has actually softened, and in the high strength steel, and the C and gamma values are calibrated according to that. So this slide moves on to show the isotropic flow, and you can see the formula here. Basically, Q and B are the parameters which again have been calibrated from dog bone cyclic tests on both high strength steel and mild steel using symmetrically strain controlled experiments. And then they were defined in the numerical model using tabulated data. You can see here how the fitting has been done, for instance, in this case, high strength steel to obtain the parameters. And these, obviously, you can see in this figure, because of the fact that high strength steel undergoes the softening, the Q value for high strength steel is negative. However, it is positive for the mild steel plate material. This is showing the comparison between our simulated model and the experimental results. In the left-hand side of this slide, you can see the strain distribution comparison between the experiments and also the numerical model. You can see how shear failure has occurred in the plate, and the stress distribution is shown there. And also on the right-hand side, we have the load displacement curve of 3 different cases, the experiments, the model only using classic plasticity without any combined plasticity, and the final one is the model which incorporates the combined plasticity in both high-strength steel and mild steel. And you can see that model closely predicts the performance and also the peak load of the different cycles, and also the cap load of the cyclic testing with an error of around 1%. On the bottom here, you can also see a comparison between cycle number 7 and cycle number 8 of the test, just showing the slight pinching mechanism which has taken place in the experiment, but also has been replicated in the numerical simulation. And the reason for that is the slight buckling happening due to shear in the plate, which you can see the failure mechanism here as well. And this only happens after the maximum story drift of 0.03 has passed, which is recommended by FEMA 461. So here we can see a comparison of the proposed dual steel hybrid steel sections with concrete filled tubular members, or as we call them, CFT members. Obviously, concrete filled members have widely been used in earthquake-prone areas due to their high strength and energy absorption capacities. If we want to drive a comparison between the cross sections, the high strength steel and the concrete in both sections act as axially load-bearing components with very low ductility, whereas the steel plates in both members act as the energy absorbing ductile component. However, again, comparing the two sections, the proposed hybrid section obviously is much lighter than the concrete counterpart due to being hollow and thin-walled. And comparison has been made using or comparing two available experiments on CFT members, and the results are shown on the right-hand side, in which it is observed that the hybrid section has a higher lateral load-bearing capacity, and also possesses an acceptable and higher ductility or deflection or deformation limit as well. Using our verified or validated abacus model, we've conducted some parametric analysis, and in order to obtain or decide on the cross-section parameters, obviously the slenderness limits have been taken into consideration. However, it is important to note that with high-strength steel tubes, the compactness rules or the slenderness limits do not apply, similar to those that apply to normal steel. So as you can see in red, and these two dashed lines, modified slenderness limits for the tubes, high strength tubes, have been used, and we've made sure that the sample specimen studied in the parametric analysis is within this limit. And the same goes with the plates. So with the plates, again, modified values of slenderness can be used. Once they are welded to high-strength tubes, they possess a different slenderness limit compared to a usual plate component. With the parametric analysis, you can see some of the results presented here. The major finding was that the maximum lateral load of the entire beam column is 3 times more sensitive to the tube's slenderness rather than the plate slenderness. And it was also observed that the peak cycle number is more sensitive to the tube slenderness rather than the plate slenderness. So reducing the slenderness ratio of tube up to 3 times basically results in an increase by up to 50% of the maximum lateral load, as you can see here in this figure. It also results in the maximum lateral load occurring up to 8 cycles later, which is a favorable observation in the cyclic performance. And finally, a study has been done on the failure mode analysis. In this slide, you can see the parametric sections have been categorized or presented based on their failure mode, whether it be axial or shear. And you can see that the shear failure, which is shown with square elements, is more favorable rather than the axial failure, because the axial failure is governed by the axial failure of actually the tubes, which is a brittle type of failure. So, and you can see the photo of this axial failure here in comparison to the ductile failure or the shear failure as we know it. So in order to propose an optimum design, we would say that a section that undergoes a shear failure would be a favorable one, but in order to make it optimum, the highest possible tube-to-tube slenderness values would be used. So this line here, the dashed line here, is actually derived between to roughly divide the axial failure and the shear failure, and to give us a good estimation of an optimum cross-section based on the slenderness of each of the components. And with that, I come to the end of my presentation. Thanks for your attention, and I welcome any questions.